There's 20 excluding me.
I think maybe still got one more. Yeah.
Okay, 22 all here. Good. Okay, so let's get started. Okay, today will be reasonably fast because there's only 2 tests to do. Yeah, basically your chi-square test and your Fischer exact test. Okay, chi-square test you can use in Excel or in R. Fischer exact test you can only do in R. So hopefully you still know what chi-square test is for. Okay, so let us go through the very first thing is this. Okay, for example, you have a question here. So this is a question inside your lab manual. a survey of 100 people found that 20 of them like chocolate cakes, 35 of them like strawberry cakes, 16 like blueberry cakes, and 21 like cheesecake. 8 of them like carrot cakes. Okay, at 5% significance, is there enough evidence to reject the hypothesis that there's equal preference of the cakes? Okay, how many of you love cakes here? Anyone love to eat cakes? Jin Xiang. Have you eaten all these 1, 2, 3, 4, 5 different type of cakes? Okay. All right. Okay. So how do we do that? So equal preference means that the expected is equal. So okay, 20, 20, 20. So this is what we have. So how are we going to do a test like this? Okay. So what we can do is we can construct a table. So this is a table. You can then calculate the observed minus expected square divided by expected and calculate the chi-square yourself. Okay, so let us do this. Okay, in fact, we don't really have to do this. Just copy the whole thing, put inside your Excel. Okay, so this will be chocolate. Let's see, what do we have? Chocolate, strawberry, blueberry, cheese. Chocolate, strawberry, blueberry, cheesecake, and carrot cake. Okay, so let's do this first and make sure you have the data in front of you for your Excel. Okay, once you're ready, then okay, similarly, what you can also do is you can do the observed minus expected square divided by expected. Okay, so what you do is observed minus the expected, square it, divide by expected. Okay, so do up to this part first. Once you are done, then you can raise up your hand. Okay, so for those who have finished, you can continue doing your chi-square statistic. So the chi-square statistic is simply the summation of all this. So you get 19.3. Okay, once you are done with this, then raise up your hands. So So we will do the next step. Lucas, Yun, Xian,
Can you show
Which one?
how you did it again?
Which one? Which one?
Like when you minus and everything.
No? So you take observed minus expected, then you square it, divide by expected. So write the equation as is. Xavier, okay?
Yeah.
Shuyun, eh?
Yep, I'm okay.
Okay, all right. So you get a chi-square statistic of 19.3. And what is the degrees of freedom here? Anyone? Okay, drop down your hands already. What is the degrees of freedom? So Saki, what is the degrees of freedom?
Is it 5?
No, degrees of freedom is the number of categories minus 1 for chi-square. So we have 5 categories. Degrees of freedom will be what? Again, your answer? What's your answer? 4, correct. Okay, so degrees of freedom 4. Okay, so how do you get the p-value for this? Okay, p-value, you will just use this formula. Basically, we use the same method which we did in the first lab. Okay, so you can take your chi-square, your right tail statistic. Okay, using this formula, chi-square dot distribution dot RT, which is the right tail. So you want to find out the right tail. X is your chi-square statistic. So X is 19.3. Degrees of freedom is 4. Just click 4. Okay, so when you have that, you end up with this. So degrees of freedom is very small. No, not the p-value. The p-value is 0.00068. Okay, got that? Okay, so based on this statistic, okay, our null hypothesis, remember our null hypothesis is that there is equal preference. Okay, alternate hypothesis means basically not equal preference, unequal preference. So based on this p-value, do we accept or reject null hypothesis? Let's have Lucas.
Hello.
Do you accept or reject null hypothesis?
Reject.
Reject null hypothesis, right? Okay. Okay, so you reject null hypothesis. Hypothesis, and then you accept alternate hypothesis. Okay. So basically, there's unequal preference. Okay, so this is one method. Okay, that means you have to calculate the chi-square statistic yourself. Okay, there is actually a faster method. You can get the p-value directly. Okay, you can get the p-value directly because actually all we want is a p-value. We don't really care about this chi-square statistic. So how do you get the p-value directly, okay, without going through all this process? Can we get it from the data itself? You can do that. You use this function, this formula called chi-square test. Okay, chi-square test, it has two components: actual range and expected range. Actual range is your observed. Okay, observed and expected range. And it will give you the p-value directly. Okay, so try this yourself. See whether you can get it using this formula. Okay, if you are there, then when you get it, then raise up your hands. Miss Yang, okay?
Sorry, can you show again?
Yeah, I'm showing you.
Oh, okay. Hang on. Just a sec.
Okay, all right. So if you're there, then you can drop down your hands. Okay, you can put down your hands already. Now, this is something that you should have known already. The observed and expected can. So my question is this: must the observed and expected be frequencies, or can they be percentage? So this is the question. Okay, how about Jermaine? Can you answer this question? Must the observed and expected be frequency, or can they be percentage?
Frequency.
Must be frequency, right? Do you know why? If I ask you to show an example of why, do you know why?
No.
No. Okay. Who can help Jermaine? Anybody can have an example of why do you actually need frequency and not percentage? Why you cannot use percentage? Or worse still, you cannot use ratio. Min Hui, any suggestions?
Is it the number of data you have? Like what percentage is just a number?
To some extent, okay, if you look at the table, right? It is from last week. Okay, so let's say if you have some data you're expected and you're observed, okay? Let's say this is category 1, category 2, and then all the way to category N. Okay, so your chi-square statistic is actually the summation of observed minus expected divide by expected, where I is 1 all the way to N. Okay, Ryan, can you put up? You can put out your hand now. Okay, and you know that your degrees of freedom is actually the number of categories minus 1. So if you look at this set of this equation by itself, based on what you learn about ANOVA and t-test, what is that one number that seems to be missing? that what is that one number that's always important in t-test and ANOVA that seems to be totally missing here? Jordan?
Significance level.
Significance level will always be there lah. Okay, so alpha will always be there. Okay, there will be always an alpha level. But there's one number that's missing inside this equation itself. Your
N.
N, right? That is your sample size.
Mm.
Right? Because remember in your t-test, this is in chi-square. In your t-test, your degrees of freedom is actually n minus 1. So sample size minus 1. Correct? But in this case, is where is the sample size in your chi-square test? It seems to be totally missing here. Right? Anybody start to realize this sample size n minus n, it seems to be totally missing here. Okay. But what I'm going to tell you is it is actually not missing, it's actually within the equation itself. That means the sample size is actually packed into this equation, just that you do not realize it. And it kind of simplifies until you do not see it anymore. Okay. So let me just give you a simulation for you to see. Okay. So I always try this all the time because a lot of students will miss out. So let's say I'm going to test a hypothesis. So my null hypothesis says that there's equal preference between coffee and tea. Okay, my alternate hypothesis will say that unequal preference. Coffee and tea. So what on earth does equal preference means? So it actually means that 50% likes coffee, 50% likes tea. That's what equal preference means. So I'm just going to do let's say I do a survey. Okay. And I do a survey, my results is that 51% likes coffee, 49% likes tea. So far so good, right? Any problem? Anyone have problem? Anyone cannot get my reasoning so far? Umaira, you okay?
Yes.
Okay. So let's try one step at a time. Let's say if I do percentage. So percentage simply means that n equals to 100 because 100 means 100%. Okay. So here I have my coffee and then my tea. Okay. My observed versus my expected. If it's 100% my survey, 51, so automatically here will be 51, here will be 49. What should I put inside my expected? These two numbers. Damien? If it's equal preference, so what should I expect?
50-50.
50-50 lor. Okay. Then let me do a type just do a p-value itself. So I do a chi-square test. Okay. And I take actual is observed over. Okay. In this case, can I reject my null hypothesis? Damien?
Accept.
You accept. Conclusion is accept null hypothesis, right? Accept. Null hypothesis. Okay. So let's say another group is very hardworking, and they, instead of survey 100 people, they survey 1,000 people. So what should my, assuming that it's still 51% likes tea, 49% likes coffee, so what should these two numbers be? Let's try Jingru.
Do you mean the observed value?
Yeah, observed value.
510 and 490.
90. How about the expected?
500, 500.
500, 500. Okay. So let me do the same statistics test again. My chi-square. Actual 510. Okay. Now this is 1,000. 1,000. So in this case, I get a p-value. See, the p-value actually changes, which means that the sample size does make a difference. Okay, this is 1, this is 10, this is 100. But do I accept or reject null hypothesis here, Jingru?
Accept.
Yes, still accept, right? Okay. So let me go continue, and let's say I have the third group that is very energetic, and they survey 10,000 participants. So what should these two numbers be, Ryan?
5,100 and 4,900.
100, 4,900. Okay. Then here will be 5,000, 5,000, right? Okay, 5,000, 5,000. And let us do the test again. Actual. Now, this is a p-value now. So, Ryan, do I accept or reject a null hypothesis here?
That's 0.5. Okay, that one we reject.
Yeah. So, I reject my null hypothesis. See the percentage. If I use percentage, right, where be it 10,000 or 100,000 people, this will be the case. Okay. But the sample size actually makes a difference. You can see that the p-value changes, even though the percentage remains the same. This is the reason why you have to use frequency instead of percentage. Worse if you use proportion, because proportion is just 1, n equals to 1. Okay. Anyone do not see this situation? So if somebody tells you that you can use percentage, please do not do that. It is wrong. The reason why I stress this a lot is there are people teaching statistics in university level that tells you that you can use percentage. Please do not listen to that. It is wrong. Show them this example. Okay. So remember this example very well. Huh? Any problems so far? So back to the question. Must it be observed? Must observe by frequency or can it be percentage? So the answer is no. It must be by frequencies. Okay, cannot be by percentage. Okay, so who is the first person I asked just now? All of you get why is it? Anybody still do not get it? If you get the reasoning, please raise up a hand. Okay, so assume that all of you gets it already. Okay, can put down your hands now. Yep, so there's actually no real tricks to using chi-square in your Excel. That's all about Excel. There's only one way to do it. Okay, actually, there's two ways. One way is to do calculate this by yourself and to get the p-value yourself. So our next step is how are we going to do it using R? So let's fire up R first. Go to your R Studio. Okay, there's no file to bring up. Okay. So let's look at the question itself. Okay. To use chi-square statistics for goodness of fit, we use this function called chi-square test. Okay. So what it really does is, for chi-square test, you give it a probability. Okay. So this is the categorical, means that let me show you. This, what does it means is, it is similar to transferring a table to look like that. Okay, let me draw the table for you. Insert table. Okay, so this is the table. So this is smokers, non-smokers. Okay, so this is your observed. This is your expected. Okay, observed, you have 7 who smoke frequently, and those that not smoke frequently, because you interview 200 people, you end up with 193. Okay, expected, you expect 5%. 5% smoke frequently, so out of 200, you expect 10. So this will be 190. Now, what does it do is, you only need to provide these cells, these 2 yellow cells. Okay, this is the yellow part. The expected you cannot provide, but you provide in terms of percentage. Actually, you can, but we tend to provide just put in terms of percentage. Okay. So what it means is, you observed is 7 and 193, but the expected frequency, the proportion, is 5% and 95%. So it's 0.5 and 0.95. Okay. Correction, you don't correct for anything, and that's where you get your answer. Okay, so let's take this, copy over, test, and then that gives you your result. Okay, try and see whether do you get the answer. Okay, when you get answer, raise your hands. Okay. Okay, then why not you redo the question 1, your strawberry thing, right? Your cake, and see whether do you get the answer. Okay, do you get 0.000686? Okay, put down your hands first, do it in your R and see whether you get it. If you get it, then you raise your hands. So this is my answer. If you can get it, then you can raise your hands. Okay, so you can put down your hands already. Okay, this is what we call as chi-square for one categorical variable because we are actually testing for one categories. But what if we want to test for independence? That means, is there a relationship between smoking and the birth weight of the babies? Okay, that's called test for independence. It's very similar to your odds ratio and your relative risk, but you can use a chi-square for that. Okay, so it's another way to look at odds ratio and relative risk. Okay, so in this case, what you have is you have smoking, the birth weight, two categories of birth weight, non-smoking, the two categories of birth weight. Okay, so what you do is you construct a matrix first. You put the four numbers in, 30, 44, 29, and 86. And you say that n rows, there are two rows. So you want to split them exactly into two rows. So it's as good as having your matrix that looks like that. Okay, two rows. Okay, and you want to test by row. So you want to test row by row. Okay, so it's actually constructing. You test one row over the other row. Okay, so this is what you do. Then you just do a chi-square test on the table itself. We can call this a contingency table because it is a contingency table. Chi-square with no correction. So let's do this and see whether do you get the results. Okay. This is how you do a chi-square for independence. So it's just basically asking you, is there a relationship between smoking and birth weight? Birth weight. Okay, if you get this result, then can raise our hands. This is actually the result that we want. Okay, so the p-value is 0.026. which means that how do you interpret this data? Is there a relationship between whether the mother is smoking and the birth weight of the baby? Charles? Is there a relationship or no relationship?
What?
Is there a relationship between the birth weight of the baby versus when the mother is smoking or not?
Not sure.
Not sure. Then what does the p-value means? Okay. So in this case, right, it is actually to test. This means that it is to test for no relationship. Okay. Means that your null hypothesis that there is no relationship between smoking status and the birth weight of infants. So the alternate hypothesis is there's a relationship. So in this case, do you accept or reject the null hypothesis? Back to Charles again.
Reject.
Reject the null hypothesis, right? Means that there is a relationship. Okay. Because remember, when you do your relative risk and odds ratio, you say that smoking has 1.4 times more chance of getting a smaller weight baby. So that is quantitative. But is there a real relationship? Maybe 1.4 could be just random, because you almost never get 1:1. So this is actually a statistic test to actually test for that kind of situation. Okay, it's more conclusive, yes or no, rather than then you use your odds ratio and relative risk to say how much is the impact. Understand? Xavier, understand or not?
No.
Okay, good. All right. So we have actually done that already. The last one that we are going to do, and say this very fast, is your Fischer exact test. You remember that Fischer exact test is very tedious to do by hand, but it's quite easy to do it here. Okay. Fischer exact test uses the same thing. Okay. What happens if the samples are actually smaller? Okay. So let's say if Fischer exact test is actually using chi-square, perfectly the same. It is automatically used when the samples, the number counts is smaller. The degrees of freedom is 1, aspect frequency is less than 1/10. But what happens if it's lower? Then you automatically use Fischer exact test. Okay. You can use a chi-square. Okay. Or you can use a Fischer exact test. So which means that, for example, let's do this. We say that this is 43439. Okay, so our table, our contingency table is 3439. Okay, which actually matches this up. Okay, so let's say this is the data itself. Okay, no problem with that. We can also do the regular chi-square statistic. No problem. Okay. Now, if you do the regular chi-square statistic, it will give you a warning error, a warning message. Says that the approximation may not be accurate, may be incorrect. Because why? The sample counts are too small. You try this, do you get these values? Or do you get the same output? So if you get the same output, then raise your hands. Okay, so in this case, how do you do Fischer exact test? All you need to do is change this chi-square test into Fischer test. The same, the rest is the same. Change to Fischer test. Unused, okay. So Fischer test doesn't use this, the rest of it. Let's do a Fischer test. And you get this. Okay. So it uses a Fischer exact test. Just remove the this as well. So this is a command that you have to use. Okay. Similarly, this is the chi-square p-value 0.149, which then you reject. No, you fail to reject null hypothesis. You accept null hypothesis. Fischer exact test also accepts the null hypothesis. It just gives you the alternate hypothesis that the true odds ratio is not equal to 1. Remember, this goes back to using odds ratio. In fact, even up to this point, right, it's still a test of odds ratio. Is the odds ratio significantly different from 1? Okay. So the alternate hypothesis means that the true odds ratio is equal to 1. Okay, so all of you got this result? Okay. Now let's go back to let's find another one. Vernice. So in this case, what does this p-value means? Is there a relationship between smoking and birth weight based on the p-values?
Yeah.
Based on this. Vernice.
Hello.
Yeah. Is there a relationship between smoking status and birth weight? They get a p-value of 0.6.
Yes.
No, yeah. So you cannot reject the null hypothesis. So the true odds ratio is actually maybe equals to 1. When odds ratio is equals to 1, there's no relationship more. Correct. So Vernice, you have to be more confident about it yourself.
Okay.
Okay? Okay, you can put down all your hands now. Now, my question next is there a problem with using Fischer exact test when chi-square can be used? Let's go back to this thing again. Okay. So let's say I did a chi-square test for okay. So look at this data that I have. Okay, this set. So it's 30, 44, 29, and 86. I do the chi-square test is correct. No problem with that. Okay, but I also can do a Fischer exact test. Okay, no problem with that as well. Okay, so Fischer exact test can be used in place of chi-square test for independence. just that it's more precise. Okay, so these two tests are somewhat equivalent. Okay, the p-value will be slightly different now. Okay, any problems so far? Any problem? Any problem?
Hi, Jordan
Yes.
here.
Yes.
Just
What?
asking, right?
Huh?
Is it possible that the chi-square would give a p-value that is smaller than the alpha, but then because of the Fisher's exact test will give about 0.01 higher, right? So let's say the chi-square gives 0.04, then will the Fisher give
Can.
like 0.05?
Yeah. Can, no? Can. Why not? Yes. Possible. That's why this is not a good way. That's why you have to know why you are using chi-square and why you are using Fisher exact test. Okay. So it is possible. Let's say if the p-value, right, for chi-square is 0.043, your Fisher exact test is going to give you 0.05. Okay. You can actually try this out lah. Let's say 49. Let's just vary the thing a little bit to this. Let's see what is the data supposed to look like. Let's go back to this table. How do we make this more of equals to 1? So we kind of push this a bit here and then push this a bit over. Okay, so let's try 44. Okay, now we reduce this by 4. Increase this by 4. Okay, then this we go to, let's say, 35. This will be 80. Let's try. I'll just play around with the numbers. 0.36. We're getting a bit better already. So here maybe just give a number, let's say 38. So here 45, 65. 0.48, close enough. Okay, so and if you do the Fisher exact test, okay, this is still not good enough, but then you can see it's getting closer. 65, maybe this we put down to 60. Okay, yeah, but you get what I'm trying to say. If it's close to 0.05, yes, the two tests can give you different answers. So Jordan, you're correct. The two tests can give you different answers on accepting or rejecting a null hypothesis.
Okay, thank you.
Yeah. Okay. Any other questions? Okay. Because if not, that's all for today. Have fun. It's just this short.
Oh, thanks.
Okay, who are?
Thank you.
Xavier, yes.
Thank you, sir.
Uh-huh.
Thank you.
Yes, Xavier, what?
Oh, nothing. I just say thanks.
Okay, thank you. Okay, go and have your lunch. You haven't had your lunch. And see you next week for the last last one.
Thank you, sir.
Bye bye, Xinxiang.